Okay, so so last time we finished up. We were talking about sequences, and this time we're going to talk about series. So right. So there's the notation that most of you have seen before, but some of you have not. So let's just start from the beginning. Given a sequence of complex numbers, given a sequence, a sub n of complex numbers, we let summation n from p to q. Right? If I write sigma a sub n equals p q, this means the sum of the a sub n, right? It's going to be a sub p plus 1, a sub p plus 2, all the way up to a q, right? So it's the sum of the a sub n from n equals p to n equals q. So this is most of you have seen this notation before. Okay. Okay. So if you have a sequence, so again, suppose you have some sequence, then we define this other thing called the sequence of partial sums. Okay, so the sequence of partial sums of your first sequence is defined S sub n is the sum of the ai from I equals 1 to n. Sequence of partial sums. Okay, so you start off with a sequence, right? So for example, right, you have some sequence, a sub n is 1 over n squared, right? So that's to say 1 over 2 squared, 1 over 3 squared, 1 over 4 squared, etc. Right? Then S sub 1 is just going to be the sum of the first term. S sub 2 is the sum of the first two terms. S sub 3 the sum of the first three terms. Right? And so on and so forth. Okay? Right, so the sequence, you have some sequence, and you have the sequence of partial sums. Okay? And if the sequence of partial sums converges, so again, so continuing along, continuing the definition, if S sub n, if the sequence of partial sums converges, I'd say Sn converges to some value s, then we write summation a sub n from 1 to infinity equals s. Okay. And say the infinite series. The infinite series a sub n sums to s. So the point is that if I say something like this, if I say something like this, the sum of 1 over n squared from n equals 1 to infinity is pi squared over 6. Okay. If I say something like that, what does that mean? Does it mean that you add these, you take an infinite number of numbers and add it together? Not exactly. What it means is that the sequence of partial sums of this converges to pi squared over 6. Okay. So to say, if I write something like this, and if I say this infinite series equals pi squared over 6, what this means is that the partial sum sequence converges to pi squared over 6. Okay. It doesn't mean that we have some way of doing infinite addition. Okay. Rather, what we're talking about is limits of sequences. Okay. The limit of a particular sequence, the sequence of partial sums. Any questions? Okay. Okay, so this thing converges is the same thing as saying that the sequence of partial sums converges. Okay. So okay. So that means that if we're talking about series, then we're really talking about sequences. And so, so for example, recall that R, or in fact C also, well, R and C are complete. Right? And so convergence of so convergence, right? A sequence is convergent if and only if it's Cauchy. Sequence is convergent if and only if it's Cauchy, and that leads to something called the Cauchy Criterion. For series. Okay. So it's this, that a series converges if and only if, given any epsilon, there exists a time such that for all n bigger than equal to n bigger than equal to that time, the absolute value of a sub k from k equals n to m is smaller than epsilon. So to check the convergence of a series, right? It suffices to show this condition, right? Given any epsilon, there's a time past which all partial tails, the absolute value of all partial tails is small. Okay, right. So why does that make sense? Somebody explain it to me. Right. This thing, for this thing to converge, is the same thing as saying that its sequence of partial sum converges. Right? Think about it for 1 minute and see if you can say, well, of course.
Can it be in like an infinite series? Like n k equals n to infinity?
Yes. I mean that will. I mean if it's true for all m that are bigger than m, all m that's bigger than n, then certainly you can take the limit of this, and that would still be smaller. Although you might, yeah. But basically yes. Okay, talk to somebody for 10 seconds or so and see if you can explain to them why this is true.
You can essentially make like any of the tails like infinitely small. Yeah, just like you can make epsilon really small, so that means.
Oh, what I was thinking is, what if you make, you know how we've done before, I think epsilon equal 2, you could take each of the A cases smaller than epsilon over ab, and then if you sum them all up, the whole thing will be, you know what I mean?
If you take it over now, epsilon over ab.
Yeah, because it's not, with other things, right, like, oh, this is smaller than epsilon over 2, and we got it together.
Okay, so
Like the m, like.
who would like to explain the Cauchy criterion? This thing converges if and only if the sequence of partial sum converges. Well, the sequence of partial sums converges if and only if it's Cauchy, right? Right. Right. Well, what does Cauchy mean? Cauchy means that given any epsilon, there exists a time such that if m and n are bigger than that time, then the size of the difference is smaller than epsilon. Right? And now I hope you're seeing it, right? What's S of m minus S of n? That basically this. I mean, you might have to put an n plus 1 here, but basically this. Right? That's to say that, right? Let's assume without loss of generality that m is bigger than or equal to n. Then this gives us m to n plus 1 is the case. Right. So for the series to converge is the same thing as requiring that given any epsilon, you can control, there's a time past which all partial tails are smaller than epsilon. Right? And that's basically, I mean, I've got an n here instead of n plus 1, but it's exactly the same. Yes, E?
Why is n plus 1 the same?
Because I can, what's the question? What?
Why is the n plus 1 there? Why is the k equal to n plus 1 there, but it's different from that k equal to n?
I mean, if you want, I can,
So
because it's true for,
oh, it's true for
it's
n.
true for all n bigger than n. You know, you could just take this n to be one smaller, and then say it's true for n plus 1 or something like that. It doesn't make any difference. Okay, so this is the Cauchy Criterion, right? Your knowledge of the convergence of sequences, gives you this thing for the convergence of a series, right? Because convergence of a series boils down to convergence of the sequence of partial sums.
So are you saying you could have equivalently have written k equals n to n?
Yeah.
It doesn't make a difference.
Yeah, it doesn't make any difference. So, okay. So, in particular, if if a series converges, then you know that the limit of the a sub n is 0 as n goes to infinity. Yes, Sam?
Is that also an infinitely if statement? Or?
No, it's not infinitely if, right? Because even if this limit is 0, that doesn't make the series converge,
Oh.
right? You may remember that this thing diverges. The harmonic series diverges, even though the terms go to 0. So yeah, it's not so simple. Okay. So if you look at the Cauchy Criterion, it says that given any epsilon, there's a time past which, if you take any m and n bigger than that, then the sum of the tail is smaller than epsilon. Okay. Now, let them be the same number, right? Let them be the same number, and you'll see, what does that say? That would say that the size of the nth term has to be less than epsilon. Right? So, given any epsilon, the Cauchy Criterion implies there exists an n such that if n is bigger than n, then the absolute value of a sub n is smaller than epsilon. I mean, it implies something stronger than that, right? If there are any two numbers bigger than n, then this partial sum is less than epsilon. But just take them to be the same number, and you get that the size of the single entry has to be less than epsilon, right? But that means that a sub n goes to 0. That's the same thing as saying that the limit of a sub n is 0. Given any epsilon, you can find a time past which these guys are smaller than epsilon. That's the same thing as saying that the a sub n go to 0. Okay. So this is called the nth term test. Right, and its contraposition is called the divergence test. Right, if the limit doesn't go to 0, then you know the series diverges. So contrapositive. If the limit of E a sub n is not 0, then the series diverges. Yes?
Can I prove backward if the limit is 0, so the series is converged?
No, that's false, right? We'll later see that this thing actually diverges, right? So no, it's not. The opposite is not true, right? If the limit is 0, doesn't mean that the series converges. So, okay, some other easy facts. If you have a non-negative series, right? So suppose that the a sub n are all, you have some sequence, and all of the terms are bigger than or equal to 0. Then the infinite series converges if and only if the sequence of partial sums is bounded. Why is that true? Why is that true? Can somebody tell me why that's true? You have a non-negative series, right? All of the terms that you're adding on are bigger than or equal to 0. See? Right? So, Adam?
Sn is monotonically increasing and bounded, which
Right.
means that converges.
Right. So, yeah, the point is that S sub n is monotonic. It's monotonically increasing, right? So, S sub n converges if and only if it's bounded. And that's the end. Okay, great. The infinite series converges means that the sequence of partial sum converges. But in this case, the sequence of partial sum converges if and only if it's bounded. Right? So we see that convergence of the non-negative series is equivalent to the boundedness of its sequence of partial sums. Okay, so next thing, we're just going to run through a bunch of tests that you've seen before in Calculus 2, but we'll prove everything now. And some of them will be better than the tests you've seen before, because they'll involve the min soup rather than the limit. Okay. So first off is the comparison test. So you have a bunch of sequences, A sub n, C sub n, and D sub n. And part one is suppose you know that the absolute value of A sub n is smaller than C sub n for all n. Okay, I'm sorry, for all n past some point. Then, if the C sub n, if the sum of the C sub n converges, then the sum of the A sub n converges. Okay. Part 2. Suppose that A sub n is bigger than or equal to B sub n, which is bigger than or equal to 0 for all n bigger than some point n naught. Then the sum of the D sub n diverges. If the sum of the D sub n diverges, then the sum of the A sub n also diverges. Okay, right. So you've got in the second case, right, if the sum of the smaller terms diverges, then the sum of the bigger terms diverges. Right. Here you've got, in the first case, if the sum of the bigger terms converges, then the sum of the smaller terms converges. Yes, Mia?
Why is that first one an absolute value but nothing else is? I guess okay, there we go. Okay, never mind, that makes sense.
Okay.
Yeah.
Okay. I mean, it won't work if we throw in, say, if we put something like this, then that actually won't work.
Yeah.
Yeah. Yeah. It's because it's true, I think. Yeah. Okay. Okay, so let's prove the first one, right? That so you have two sequences, right? And one of them is a bunch of non-negative numbers, right? The C sub n are all non-negative numbers, and the A sub n are such that all the absolute values of them are smaller than those numbers. Okay, and you know that the sum of these bounds converges.
So we are assuming C sub n is positive.
Yeah. So if you see something like this, it implies that these are real numbers, right?
Yeah.
And they're going to be non-negative because this is bigger than or equal to 0, right? So it's implicit in the description. Yeah. So this tells you that the C sub n are real numbers and that the C sub n are all bigger than or equal to 0. But it's already in there, so we don't usually write it out. Okay. Okay. So so let's prove the first one. Right. So what do we want to show? Okay. We want to show that the sum of the A sub n converges, right? So let's use the Cauchy criterion. So use Cauchy criterion. We want to show that given epsilon, there exists a time such that if n and m are bigger than that time, then the sum from n to m of the A sub n is smaller than epsilon. Right. This is the Cauchy criterion. Right?
Should be A sub k.
Oh, I'm sorry. Yeah, A sub k. Thanks. Okay. Anybody see how to define the n? Anybody see how to find the n? we know that the C sub n converge, right? We know that the sum for the C sub n converges. So, right, so we know, right, that there exists some n1, say, such that if n and m are bigger than n1, then the absolute value of the C sub k from k equals n to m is smaller than epsilon. Right? So what do we do? What do we know about the C's and the A's?
You make the n bigger or equal to n1.
Okay, right. So take, so if n and m are bigger than n1, we know that the sum of the A sub k's from k equals n to m is smaller than or equal to the sum of the C's. Well, actually, we have to do something a little bit. We have to say something else, which is by the triangle inequality, this is smaller than the sums of the absolute values of these guys, right? Because I want to use this to get this thing smaller than that thing, right? Which is smaller than the sums of the C sub k's from k equals n to n, which is smaller than epsilon. Okay, but notice that this actually only held past n naught, so let's throw that in too. Right? We need to make sure that we're past n naught. So if n and m are bigger than the max of n naught and n1, then this is true. Yeah, Fernando.
I'm just curious about the. Oh, never mind.
Okay. The C sub k are all positive numbers or non-negative numbers. So with the absolute value, it's the same thing with or without the absolute value. If that was your question. Okay. Any questions? Right. So if you have a sequence that dominates the absolute values of another sequence, then if the sum of these bounds converges, then the sum of the controlled terms converges. Okay. So for example, right, later we said that this thing actually equals pi squared over 6, right? Okay. So if you had, for example, if you had some sequence of, say, a sub n are all a bunch of complex numbers, right? And suppose you know that the size of the complex numbers are all, the size of the complex numbers is 1 over n squared, right? That would tell you that the sum of the complex numbers is going to converge, right? Because it's dominated by the modulus is dominated. The modulus is 1 over n squared, and the sum of 1 over n squared converges. So this tells you, you can choose any complex numbers whose size is less than 1 over n squared, and that series, the sum of them would have to converge. Okay. Now for the other part, right? So here what we have here is not all that different, right? We have numbers where this guy is bigger than this guy, and this is bigger than 0, right? And so from part 1, so proof of 2, from part 1, we know that if the bigger guys converge, then the smaller guy converges. Right. If the bigger guy converges, then the smaller guy converges. Right. But just take the contrapose. That's equivalent to saying that if the smaller guy diverges, then the bigger guy diverges. Right. And so that's what we're saying. Take the contrapositive. Okay, so comparison test that you've seen before. Okay. Any questions about that? Okay. Next thing is called, let's just call it, it didn't have a name on it, but let's just call it the lacunary theorem. And this is actually due to Cauchy. So suppose you have a non-negative, non-increasing sequence. Non-negative, non-increasing sequence. Okay, so the terms are, basically decreasing. Okay. Then, and suppose you want to check the convergence of the corresponding series, then it suffices to look at terms with some gaps in them. Okay. You don't have to check the sum of the full sequence, but you just check the terms at certain points of the sequence. Some of the terms at certain points in the sequence. This is a lie, but now it's true. Okay. Multiplied by this number, by the corresponding index. So you only have to look at a to the 0 plus 2 a sub 2 plus 4 a sub 4 plus 8 a sub 8 plus plus plus. Okay, so you only have to look at terms. You don't have to consider all the terms. You don't have to know all the terms. You only need to know the terms that correspond to powers of 2. Okay, and that's why this is called a lacunary sequence, right? Because there are gaps, right? Lacuna gap. Right? Okay, so the sequence converges if and only if this lacunary sequence converges. This is a kind of cool and pretty useful theorem. We're going to use it a lot in the next few minutes. Okay, so here's the proof of it. Let S of n be a1 plus a2 plus a sub n. Right. So the partial sum for A sub n's, and let T sub k be A1 plus 2A2 plus 2 to the k, A sub 2 to the k. So it's a partial sum for the other sequence. Okay, so here's the point. Observe that for any pair nk such that n is less than 2 to the k, we have S of n is less than or equal to T sub k. And conversely, we'll observe that whenever n is bigger than 2 to the k, we have S of n is bigger than or equal to 1/2 T sub k. Does everybody see why this makes the convergence of the series equivalent? Right? Look, if we have this relation, right? If the S of n's diverge, right? If the S of n's diverge, right? If these guys are unbounded, then the T sub k's are going to be unbounded. Right? Similarly, if the T sub k's are unbounded, then the S of n's are going to be unbounded. Right? And so if these guys diverge, those guys diverge. Right? If these guys diverge, then these guys diverge. Right? And so their convergence is equivalent. Right? If these guys converge, then these guys are going to converge. And so on. And we haven't proven this yet, but what we're going to use is once we've shown this, then just by comparison test, we'll get that we'll get this equivalence. Okay, so let's see why this happens. Let's see why this happens. Why? Well, you think, well, S of n is, of course, A1 plus A2 plus A sub n, right? Now, n being less than 2 to the k, I'm going to add on some more terms. Oops. A sub n plus A sub 2 to the k plus A sub 2 to the k plus 1 minus 1. So I go all the way up to, I throw in all these terms just before the 2k plus 1th term. But that thing is less than or equal to T sub k, right? Because if we look at A2 plus A3, did I mess it up? These guys are non-increasing, so they're decreasing in size, right? These guys are decreasing in size, right? So a sub 2 plus a sub 3 is smaller than, yeah, right? Yeah, smaller than, right? This is smaller than, this is A1. A2 plus A3 is smaller than 2A2, right? And then the next 4 terms are smaller than 2 squared a sub 4, blah, 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 smaller than 2 to the k, a 2 to the k. Right? Okay, so let me make it a little bit clearer. A1 plus A2 plus A3 plus A4 plus A5, A6, A7, A8. Blah, blah. Okay. This thing, of course, is A1. Now these guys are decreasing, so this is smaller than 2A2. I take the next 4 terms. This is smaller than 4A4, and so on and so forth. Right? So you just block them off. You just block them off, right? In dyadic combinations. Right? So you take the next 2 guys. You take the next 4 guys. You take the next 8 guys. Right? This will be small. This thing will be, the next block will be smaller than 8A8. And so on and so forth. Okay, and so you end up with what you end up with is T sub k.
What about like the tail end of it, where you added like a sub 2 to the k all the way?
Yeah, so this is just the last 2 to the k terms. Right. The next term here that I didn't get to is a to the 2 to the k plus 1.
Mm-hmm.
Okay, so I'm just taking the next 2 to the k terms.
I got it.
Okay. Okay, so you see that S of n is less than tk. And then the other way around, basically, you just do something similar. You say, well, look, if I look at something like this, well, I know the first term is bigger than 1/2 A1, right? The second term is A2. If I take these guys, this is bigger than 2A4, right? Because they're decreasing, right? They're decreasing. This thing is bigger than 4A8, right? And so on and so forth, right? And you see what you get would be 1/2 T sub k, right? You're going to get 1/2 T sub k, and so you get the other side, A sub n with the right n and k. A sub n is bigger than 1/2 tk. So that gives it to you. If the Sn are unbounded, then the Tk are unbounded. If the Tk are unbounded, then the Sn are unbounded. Sorry, there should be an S. Okay. So this is pretty cool. I mean, it kind of makes sense, right? If you have a sequence that's non-increasing, you don't really need to know the size of everybody. You just take the first, the second, the fourth, the eighth guys, and everybody else is trapped between these guys anyway. And so you don't have to know their values. You don't need to know exactly their values. So this thing converges if and only if the lacunary sequence converges. Any questions?
So then you just apply the theorem that we just did.
Yeah. So we'll use this theorem, this lacunary theorem.
We apply the comparison test.
Yes, we'll use the comparison test. That's right. Use the comparison test to finish this. Right. Okay. So the next theorem, I'm not gonna explain because I'm pretty sure you've all seen the proof of this in calculus. That if you have if x is between 0 and if x is between 0 and 1, then the sum of x to the n from n equals 0 to infinity is 1 over 1 minus x. Right. And if, of course, if x is bigger than or equal to 1, then it diverges. So I'm not going to prove that. You've all seen it before, I'm sure. Instead, let's go to something else you've seen before, but we're going to prove it using the lacunary test, just for fun. P series, summation 1 over n to the p converges if and only if p is bigger than 1. Actually, take 1 minute and try to apply the lacunary test to this series. So I assume that p is bigger than 0, because if p is less than 0, then it clearly diverges. It would diverge by the nth term test. So what happens, right? Lacunary test says that this thing converges if and only if what converges? Summation 2 to the k 2 to the k, p, 1 over 2 to the k p. Right? Converges. Right? Which I'm going to rewrite as 2 to the 1 minus k. I'm sorry, 1 minus p times k. Converges. Okay. But you see what this is, right? This is a, yeah, Alex.
Wouldn't it be k? I'm confused why you're substituting out in for 2, right?
So for n, we take 2 to the k, right? So we have 2 to the k, 1 over 2 to the k to the p.
And then you have 1 over n into the p, so that should change to 1 over n to the 2p.
So this 2 to the k to the p is 2 to the kp.
Right.
Right?
Oh, so you're instead of n, you're writing 2 to the k?
That's right.
Okay.
Right? So instead of taking the sum of all the terms, you only take the terms that are powers of 2. So, right, so like k, this converges if and only if this converges. Okay, but this is the same thing as this, right? And then you see that this thing is, just this thing to the kth power, right? So it's a geometric series, right? This is a geometric series. So it converges if and only if 1 minus p is less than 0. Right. Right. We need this thing to be smaller than 1. Right? We need 2 to the 1 minus p to be smaller than 1. In other words, we need 1 minus p to be smaller than 0. And so that's it, right? So this thing converges if and only if p is bigger than 1. Okay, right, so this gives you some sort of boundary, right? You see that 1 over n diverges, right? This diverges, but 1 over n to the 1 plus any tiny number converges. Right? So for any tiny number, right, just slightly bigger than 1, then you have convergence. So it gives you some sort of a boundary. Let me see if I can fit in the next.
Well, if it's 1, so if p is 1, isn't it just a constant function? Is that not convergent?
It's 1, but then it's just 1 over n, so it's unlike series, right?
Say it again, John.
So you have if p, so say p does equal 1,
Yeah.
and then you go down to like that where you have the bound, the 2 to the 1 minus p.
Yeah.
So you just get 2 to the 0, so you have
That's
1.
right.
1.
You'd have the sum of 1, which would be triple, right? Because
Oh,
you'd have
yeah,
1
totally
plus 1
forgot
plus 1 plus 1, which would
Yeah,
diverge.
So
Yeah. Yeah, the terms converge, but the sum diverges.
yeah.
Okay. Let me see if I can squeeze in one last and kind of cool result. At least I think it's cool. I don't know how you all feel about it. Yeah, I wouldn't say that I feel like everything or much of today was cool, but at least this one thing is cool. Okay. So something similar. If you, this thing is going to converge as long as you have p bigger than 1 here. Okay. So for example, right, 1 over n log n diverges. Right? But 1 over n log n, to some power bigger than 1 is going to converge. Okay. So right, like you know that 1 over n diverges, right? And you know that if you multiply this by any, if you throw in an n to the epsilon where epsilon is bigger than 0, then it converges, right? But what this is saying is that if you throw in logs of n here, then it's still going to diverge. Okay, so it's like you're pushing the boundary. You're pushing the boundary. You're finding, in a finer sense, where the boundary lies between convergence and divergence. Just a second. Yes.
I thought in the book they made a big deal of like there's no boundary.
Right. In fact, but there is no exact boundary, but this is you're getting some sense of a boundary. Yeah. So yeah, I mean, only within a sort of limited sense is this a boundary, right? Because we're restricting ourselves to guys that look like this. In this case, 1 is the boundary, but it's not an exact boundary. Yeah. Okay. So so just to get through this quickly, again we have decreasing. Again we have decreasing terms. So we can apply the lacunary theorem. And we see that we have to consider the convergence of 2 to the k, 1 over 2 to the k log 2 to the k quantity to the p, right? So take 2 to the k times the 2 to the k terms and 2 sub k terms, 2 to the k terms. Right. Of course, these things cancel off, and we can pull the k out. Right. So you get summation 1 over k log 2 quantity to the p, k from 2 to infinity. Right. And we can pull out the log. The log 2 to the p is constant, right? And we get summation k from 2 to infinity, 1 over k to the p, right? Which converges, right? Which converges if and only if p is bigger than 1. So this gives you a finer sense of the boundary, even though there is no precise boundary. The boundary between convergence and divergence. I'm not going to, I don't think I'll talk about the number e. Just read that part about e yourselves. Next time we'll talk about convergence tests for series, root and ratio, et cetera, et cetera. Okay.